binomial. Binomial distribution. Here, let a random experiment, or we can say Bernoulli experiment. What does it mean by Bernoulli experiment? Bernoulli experiment having success and failure. Success and failure. The Bernoulli experiment repeatedly, n number of times it has been repeated. Okay, n number of times had been repeated, or maybe n times your Bernoulli trials has been repeated. Here n being a finite, you can say. Okay, n number of trials, you can say. Number of trials. And you can say it is a P is a success for each and every trial. So here, every experiment, your probability will be constant. Okay, probability of a success will be constant for each and every trial. So now, the Bernoulli binomial distribution exists. The Bernoulli distribution exists if there are the probability of X successes. Means that the probability of X successes from if let it be, there are X successes, definitely n minus X failures will be there. We'll go to see, there are total n number of trials. Let it be n successes are there, definitely n minus X failures will be there. Okay, that is means which will be like that, you know, probability of success, failure, success, and so on, success, failure, success, like that. Because we know that every trail is a independent. So this can be written as P of S, P of S, P of S, P of F, and so on, P of S, P of F, and P of S. So this can be, success will be P, Q, and so on, P, Q, and P. Okay. So here, as per this information, okay, as per this information, so n minus X failures and X successes. So as per this information, this will be successes are X successes and n minus X failures. Now, you have X successes and definitely n minus X failures out of n trials, right? N trials. So now, in how many ways you can, how many ways you can draw your successes? Okay. So n c x ways. That's why your mass function of this binomial distribution, that is probability of X is equal to X, will be ncx p power X q power n minus X. Okay, so this can be written as, you can expand this one. You want to expand this one, q power n, nc1. First trail is q power n, second is nc1, q power n minus 1 into p, third is nc2, q power n minus 2 p square, and fourth one is, and so on, final one is p power n. all are the successive terms of the binomial expansion. Can I write a binomial expansion? This one is Q plus P whole power n. Got it? Q plus P whole power n. So here the remark is, or maybe because it's a, we can say it is a probability mass function. X is equal to 0, 1, 2, and so on, n, because n being a finite, and 0 otherwise. So now, if summation x is equal to 0 to n, p of x, what you can get? Summation x is equal to 0 to n, ncx, p power x, q power n minus x. Definitely it will be your q plus p whole power n. That is 1. Total probability is equal to 1. If there will be another remark is there. Let us suppose that n trials constitute an experiment. If the experiment is repeated capital N times, if the experiment is repeated, capital N times, okay, then the frequency function, not the distribution, frequency function, that is f of x is equal to capital N into p of x. This is your frequency function. Or you can write capital N into ncx, p power x, q power n minus. Even this here also you can write capital N into q plus p whole power n. Okay. Actually, the physical conditions of this binomial distribution is each trail resulting in 2 mutually disjoint events. Mutually disjoint, I'm telling you, mutually disjoint in a random experiment. Mutually disjoint. This maybe you can say it is a success, and this is your failure Q. Success P you can write, and failure Q. And the number of trails are finite here, n being finite. Third one is trails are independent. Trails are independent. That's why you get p power x into q power n minus x. And success is constant for each and every trail. I can say it is constant. Constant for each and every trail. Now we can draw the moments of this, derive the moments of what is a binomial distribution. Moments. Either you can derive using what is a moment generating function, or directly. We can solve in the direct first. Then after that we can solve it is by using, we can derive by using moment generating function. Mu1 dash is expectation of x, that is summation x ranging from 0 to n, x into p of x. So this will be summation x ranging from 0 to n, x into ncx, p power x, q power n minus x. X ranging from 0 to n, x into, can I write this one? N factorial upon x into x minus 1 factorial into n minus x factorial. P power x into q power n minus x. So XX will be cancelled. So this again I can write summation x ranging from 0 to n. So x ranging from 0 to n, we cannot say that it's x ranging from 0 to n here. Maybe I can say like I can write like this: n into n minus 1 factorial upon x minus 1 factorial into n minus x factorial, so that x ranging from 1 to 1 to n, and this is p power x. I can write p into p power x minus 1 q power n minus x. So n and p are the constants, and summation x ranging from 1 to n, n minus 1 c x minus 1 p power x minus 1 q power n minus x. So this entire thing will be, it is, you can write q plus p whole power n minus 1. So this will be 0. Sorry, so this will be 1. So your expectation of x, that is mean of the binomial distribution, is n into p. So your n is number of trials and p is your success. Coming to the second movement, that is mu2 dash, expectation of x square. So if you know that expectation of x and expectation of x square, then only you can find out your variance, that is mu2. Then only you can find out your mu2. Hope you remember. So for this, summation x ranging from 0 to n, x square ncx p power x q power n minus x. Okay. So can I write this one? Summation x ranges from 0 to n, x square can I write x into x minus 1 plus x. Then n into n minus 1 into n minus 2 factorial upon x into x minus 1 into x minus 2 factorial into n minus x factorial p square into p power x minus 2 into q power n minus x. Okay. Or else this entire thing you can keep it in mind. This entire thing, maybe I can write into, this is same thing, ncx p power x q power n minus x. So in the next step I can write summation x range from 0 to n, x into x minus 1 into ncx p power x q power n minus x plus summation x ranging from 0 to n, x into ncx p power x q power n minus x. So now this entire thing you can apply here. What you can get? Summation x ranging from 2 to n, n into n minus 1 into p square, then n minus 2 c x minus 2 p power x minus 2 q power n minus x plus this entire thing, you know that np, that is x into p of x, it is your expectation of x. So from this I can write n into n minus 1 p square, this entire thing summation ranging from 2 to n, it will be q plus p, this one, and you can write the summation here, summation n ranging from 2 to n. So this entire thing will be q plus p, sorry, q plus p whole power n minus 2 plus np. Okay. So you know that expectation of x square and as well as expectation of x also. So definitely based on the known notation, that is mu2, that is mu2 dash minus mu1 dash whole square, or variance of x is equal to expectation of x square minus expectation of x whole square. So that is expectation of x square is your n into n minus 1 p square plus np minus np whole square. So I can write n square minus np square plus np minus, sorry, n square p square. It n square p square. So n square p square will be cancelled. You can get here n p square plus np. You can make np is a common. So it is, sorry, minus np square, right? Minus np square. Then you can get 1 minus p. So that will be npq. So your variance of x is npq. So just to remember, mean of binomial distribution. Mean is np and variance is npq. Okay. So this you remember in your mind that for binomial distribution, what is mean and what is the variance of a random variable. Binomial variate, if it is x is a binomial variate, what is mean and what is variance? Okay. So after that you can find out the beta 1, beta 2, that is skewness and kurtosis and all. I think not necessary, but you can remember. You can remember that beta 1 is equal to mu3 square by mu2 cube. That you can find out your beta 1 in binomial distribution 1 minus 2p whole square by npq. And coming to the beta 2, that is mu4 by mu2 square, that you can get 3 plus 1 minus 6p cube upon np cube. And gamma 1 is the square root of your beta 1, that is 1 minus 2p by under root np cube. And gamma 2 is your beta 2 minus 3. That's simple, 1 minus 6p cube by np cube. So can we find out the moment generating function of binomial distribution here? MGF of binomial distribution. That is mx of t is equal to expectation of e power tx. That is what the moment generating function. So I can write summation x ranging from 0 to n e power tx ncx p power x q power n minus x. Can I write this one? Summation x ranging from 0 to n ncx p into e power t whole power x q power n minus x. Okay. See, if we write this entire thing with the summation, what we write? Q plus P whole power n. Right? Here, in the place of P, what you have? P into e power t. Can I write this one is Q plus P into e power t whole power n of your, this is your moment generating function of the binomial distribution. Similar way, characteristics function of binomial distribution, simple. The characteristics function of binomial distribution is phi x of t is equal to expectation of e power itx. That is summation x ranging from 0 to n e power itx ncx p power x q power n minus x. This can be written as summation x ranging from 0 to n ncx p into e power it whole power x into q power n minus x. This can be written as q plus p into e power it whole power n of your, this is your characteristics function of binomial distribution. Okay.